Let's see who is joining. Can you hear me? I'm right now from Ventspils location. So, at least someone is joining. Hopefully others will catch up later. So, yeah, probably because many people might have work at this time, but so, but there are some who actually would need to join at this time, but fine. So if nobody comes in person in Ventspils location, then probably will not do these sessions in person in Ventspils. So can you see and hear okay, and here okay, plus minus? So anyone in the chat? My plan is soon to start posting the surveys about the exam times. So we'll have probably exams in multiple locations, and yeah, you will need to vote for dates probably, and then I will go to those locations and we'll do exams in person. So there will be tests and things like that. Yep, great, thanks. At least somebody is responding. Thank you very much. So, yeah, today we'll probably make it a little bit shorter than other times because I also a little bit too busy again. But what I want to cover some really important topics, which are so yeah. Let's just dig in a little bit. So last time we talked about the autoencoders and variational autoencoders. Variational autoencoders are very cool, especially the quantizing variational autoencoder. So definitely, please check out yourself because of the limitations of this course. We have a little bit less time to go very deep in detail. So VQ. So was it VQ variational autoencoder? I think it was named like that. Let's double check. Quantizing variational autoencoders. Those are some of the state-of-the-art GAN models are based on that. Also, if you're interested in continuing to study these topics in the January, yeah, this is the right. In January, we'll start a new group where we will go again from very beginning, but that will be even deeper than this. So, and then definitely we will cover these types of autoencoders as well. So today, we actually have some topic which is really, really popular because many people already are using it quite easily. Pre-trained versions. So, for example, most of the people have seen the YellowRobot type of model, and it's actually getting better and better and better. So we can actually talk also a little bit about the YellowRobot and the metrics they use and data sets they use. Then we'll go back to this what we need to talk. So the YellowRobot over the years, actually funny that they don't print the years, but it's about like 10-year period. About 10-year period, they so this is like the most popular library for object detection. How it looks like. Let me give you some examples. It has a lot of built-in classes, like for example cars, people, all sorts of objects. So if you feed the image, you probably could get something like this out quite nicely. Let's actually check. And the dataset which they use is a COCO dataset. I think the COCO dataset also gets better over time. At least I believe so. There is a COCO competition, and they they improve that dataset every year, as far as I remember. I need to double check if this competition is stopped, because many AI competitions already are stopped and then new comes in the place. But this is like the most popular object detection framework in the world. It's very easy to use. It was, by the way, the history was that initially it was based on C++ Darknet, it was called, and then I think last maybe 3 versions or 4 versions, they are now PyTorch. So everything is PyTorch nowadays, and the acronym is so it was something like just you look only once or something like that. That was the name of the model. we will at the end maybe talk a little bit more how it works, but there are multiple flavors, multiple ways how to do these things: the object detection, the instance segmentation, and all sorts of other things. So let me see, what was the you only look once. You only look once. Yes, that was the naming of that. Okay, so this is object detection, where we draw the boxes around objects. And the one thing you already start seeing here, and we'll talk about this more, is that any image can contain arbitrary number of objects and boxes. So this is really cool, because it means that your model have some kind of mechanism to give you out variable length of outputs. So we will see variable length of outputs next week when we will talk about recurrent neural networks. But here this is the first attempt of some model which gives the output, which can change the number of the outputs, basically. So that's something different than what we looked so far. So, but let's start simple. So this is the most popular one, but from the simple side, let's go then. There are the classification, right? So this is the first task of classification, where you give the probabilities of what you see there. And actually this image is not really great, because like almost never would happen this kind of situation. It is very how to say, like, it's kind of foolish to think that this is the way how classifiers work, because so why it is, so this is because the categorical cross entropy and softmax, both of those functions, they want to empathize. So basically what they want to do, so the cross entropy and the softmax want to make sure that your outputs are the one hot encoded vectors, basically. So, and what it actually entails is that it will tend to predict, in this case, if I have sheep, cat, dog, horse, it will never do what it shows in the picture. So basically, it will never try to, even if there is a dog, if there is like 2 dogs and 5 sheep, it will just try to say that sheep is 99%, basically. So it is never trying to predict multiple classes at once. So there are ways how to change it, like for example use KL divergence for instead of cross entropy. But if you put in numbers in cross entropy, you will quickly find out that it only favors one class at a time, and that's only. So let's actually check. We had some images more, show you more stuff. So again, if I have this kind of model which predicts only one thing, so it's basically something like that. Classifiers, right? The softmax plus CCE, or actually you could use you could use the some kind of norm max plus plus KL, and then it would be option to predict multiple things at once, and the second option is actually not that much explored, so I don't think there's a huge scientific value of doing this, but still this is this could be explored better in scientific literature. So, and if you do that, then there are some cool methods to actually also segment image. So what we are talking about here is still classification. And what I can do, I can use class activation maps basically. Activation maps. And if in my image I get a prediction of, so how it works, if I get a prediction of my image of road, then what I can do, I can say in the, so basically so how it works is actually quite simple to do. So for example, if I have the output predictions of y prime, so there would be y prime, let's say, just make something up, so road and pavement and road and pavement, and then for example it will give me 0.9 and 0.1 like that. And what I say, so, and then I decide, so what I decide is to make something completely opposite. So I say that instead of in the first picture where it tries to predict that the road is what I say that I see opposite. So specifically, so opposite. And then what I do, I calculate the derivatives, gradients, through the whole model, and then basically what I can visualize is so for each pixel we actually could visualize that. So there would be d loss, yeah, with regards. So I mean d loss with regards to x, but it's the x is kind of not really x. It's a sum of all of the features in every layer. So basically. And I visualized that, and then and this was actually, I visualized the maybe average or sum, yeah, sum of absolute values probably. So that's what I visualize, and I get output like that. And this is actually a really cool method. So you can kind of like look into the black box models and understand what they think, how to quote unquote. So basically you can see which pixels, which areas in the image are responsible for doing the classification. Because I'm sending the opposite signal, I'm getting a huge error from all of the areas on the picture where I have the classifying features, and then I visualize it, and it actually works super nice if you do it correctly. So basically in this case, Again, these samples are a little bit over-exaggerated because, as I say, it will never be beautifully just two images. It will be working very well on this one class. So for one class it will work great. For many classes it will not work great if it's trained with cross entropy. So here on the top part as well, like cat and dog. So actually this goes together with this basically very nicely. So cat and dog, right? If I'm reversing the features, I get cat and then I get dog. And this is something that can be actually used as the segmentation. So and you can imagine how this is cool. So if you don't have, for example, labeling resources, somebody drawing these masks. So to do the segmentation properly, you need to draw masks like these, right? So don't have those resources. Then if you use some kind of large vision models, we'll talk about them a little bit later as well, like the llama vision, the clip model, all sorts of blip model and others. So they could give you the captioning of the image. So it says, let's say in the image is the the dog or cat, right? And then you train your classifier, and then when the classifier is trained, then using class activation maps, you could actually extract areas where the object is located, and all of that is given for free, so to say, for you. So you just choose the right architecture, right loss functions, and the right methods, and you get additional value out of this. So even classification, image recognition, or classification is a great tool for exploring the segmentation features. So then the next is the semantic segmentation. So actually, maybe we can add some notes here. These are the classifiers. Yeah, classifiers. There could be the efficient net, ResNet, DenseNet, right? All of those guys. We already know how to build them. So all of these are these. And then, of course, these plus class activation maps, cam, gradcam, and so on. So these are these. Then the semantic segmentation. So these, as you see in the picture, so you need ground truth labels, ground truth masks for each of the object, but you see that there is a difference from instance segmentation, so that the sheeps are all at the same blob. So it is trying to distinguish between objects based on their texture and structure locally, but at the same time it does not care if there's multiple objects of same instance. And this functionality is actually very useful in many cases. You can even then do the blob detection and get the output, get these objects out. And this is the most reliable method actually. So this would be most reliable. Hopefully I wrote it right. No, I didn't wrote it. So fix it. Yeah, reliable segmentation. Because it is really simple. It is working on pixel level. Basically, there's no crazy systems that make it unstable. So basically, and this is UNet. There's different variants: DPLAB, FCN, fully connected neural networks, convolutional neural networks, and so on. So those are those, and how actually it in reality it looks like. I had some picture. So basically, you have this ground truth mask, and in reality, the prediction is also not. It's never that crisp. So basically, if you have ground truth mask of here the bicycle rider, right, and then the predictions looks usually something like that. It is rarely perfect, but it is very good. So you still can use it to do all sorts of things that can. For example, we have this project where we segment wooden planks, for example. So this is that. Then the object detection, again, so there is the pixel level masks, yeah, pixel level masks. And then for the object detection, we have something else. And this is this is sometimes also called instance segmentation. Do I have some maybe other picture? But this is object detection because it only have the boxes. Do I have it somewhere? Yeah, this will be fine. So now this is the YOLO. So this is the this will give us not pixel level. So just give us the boxes, basically bounding boxes, and confidence. So, and here the most popular one is YOLO. There are some others, but that is the main one. Like, what are the others? Let me think. So there's I think there's SSD, if I'm not mistaken. So something like that. So these have some problems. For example, of course, we don't have these pixel maps masks, but also there is an algorithm and method how to try to predict the right number of boxes, and this is very hard to try to make sure that this works well. Also, there is limitations. For example, if there would be many dogs in distance, small looking dogs in one area, it will just detect one of them, because there you will see that there is a limitations. It does not give you all of the objects on the image. So that's another problem. And then instance segmentation. So this is usually, it actually goes also with boxes, not only with the pixel segments. So usually it comes with boxes plus the pixel masks. And then these are models like faster RCNN. Yeah, I think it was called like that, and models on that like, yeah, so something like that. So there are lots of models like those as well, but these are even less stable than previous. So the UNets and the semantic segmentation more stable than object detection, and then the instance segmentation. Even though they are not perfect, the later two, they are still really good. So in many cases you can still use them. So, and if you have any questions, write in the chat. Great, thanks for comments so far. So yeah, so this is the playing field. So these 4 types of methods for segmentation, specific naming of that. So the next, about the YellowRobot, there is, maybe you did not pay attention on this area. So there is the metrics for these, especially for these object detection models, are really messed up basically. So they are still using those metrics, but this is not great in my opinion. So what it is, so this is the mean average precision, and there is also this tricky number there. So this is from 50 till 95. Okay. So this is actually how they calculate it. So they calculate it as a mean value. Okay, can I put it enter here? No, that's not cool. So mean value of, let's see, can I get it in the new line? Okay, let's try again. Yes. So mean value of average precision of all classes. You know, just the accuracy. Maybe I should just write it as accuracy of all classes at threshold 50. So then accuracy at all classes at threshold 55, then accuracy at all classes at threshold 60, and so on. So, and you go up till the 95. So it's already giving less realistic life. So basically, in your real life application, this is useless. You need specific number at which you predict your objects. Like, I cannot implement system where I will have prediction of objects based on so the confidence will change over time. So maybe I can do it, you know, like it did not predict any object, then I will reduce the confidence, but then I will get a huge number of false positives. So this is totally nonsense. So there is also sometimes they use something like mean average precision at let's say 70% threshold. So everything that's about 0.7 confidence, that is the predicted box, for example. So that makes sense. So this is okay basically. But the all others are really messed up metrics, and especially the most messed up is just mean average precision, which means everything from 0 till 100 basically. So I don't know, like totally useless basically. If anyone can argue against me in the chat, would be interesting to study it more. So, but you see already these numbers are not really that great. So, let me see. So there is, even with that average precision threshold, the numbers are like you see 55%, and this is yeah. So how did they do this? So the average precision. So I think it's just like if there is a confidence and also maybe overlap of the boxes itself, IOU. So we will talk about IOU about a little bit later as well. So these are these metrics, how they measure it. Maybe you could actually as well start talking about metrics now. So the metrics, how they measure it properly. I talked about this average precision metric, where so basically if I identify that object exists in the right place and the right category, then I have the right accuracy. So, but how to identify if the object actually exists in the right place? So we use the IOU. It can be usually it's in the pixel space, but it can be also on the box space, right, in the boxes. So they had some more pictures of that, how the IOU works. Okay, here I think this one is good. So work. Okay, cool. So I have some IOU examples. So false negatives. So IOU. So the red box is the ground truth. So it says that yeah. So it says that there is the blue box is prediction. So it says that there is no bird in the image. False negative 0 0 IOU. So if it's a little bit overlapped, then there is something. If it's like greatly overlapped, then there is 96% overlap. So that's a common metric to use. Also, actually, like in the pixel space, box space, whatever, I prefer this way better than mean average precision. Mean average precision is such a misleading metric. So that's that. Okay, so let's then start talking about how to make it in the most stable way using the UNet type of approaches. Let's see. So, and we'll build these just in a second. So the UNet type of models work something like this. We have the inputs in RGB and the outputs are in multi-channel class representations. So there is another example of how to look at this. Let's load it. So we have input image and output have, let's make it smaller. So the output have these channels where you see that there is a channel for person, then there is another channel for bench, for grass, and then there is another channel for cat, and it says that there might be cat here, for example, but it can be also all zeros. So we define ourselves the outputs, but we also need the masks. So somebody needs to do the masks in some format that can be read, and then we can do it. And from the architecture standpoint, it looks very similar to what we did last time with the autoencoders and the variational autoencoders, but here are some key difference, and you see these lines. And as you know previously from the resnets, dense nets, and so on, lines usually means mathematical operation. In this case, it means the so addition, or it can mean also concat. And the idea is that that these models copy features from the input to the output directly to those convolutions. And that is really cool, because basically what it can do, it can learn to do this task, but it can just copy whole structure. Like if I have a structure of person here, so this, right, it's not actually here, but like for example here I have a car, and there is a car objects. I don't need to learn to reconstruct objects. I can just copy the area of object from the input to the output, and model can just learn the segmentation task alone. So all of those things are really cool. Also, you see that architecture is similar to one I showed you last time with upsampling, not with transposed convolutions. Nowadays, many models use upsampling. All other layers I think you can recognize. So far so good. The way how you train this thing is basically again using softmax. And again would be nice to use some kind of weighted softmax. If you have just two classes, then you use binary cross entropy. I will open the task and then we will look at what kind of the data set I have there, and then we will choose what we use then. So yeah, let's maybe a few more words about architectures. Let me. So far so good. So we have the UNet architecture. Again, different way to looking at it as in previous image. Okay, so in this case, it is written up convolution or transposed convolution, but it can be also upscaling, bilinear, or so on. So and these lines are additions or concatenations, but like maybe I can even tell you now that mathematically it doesn't like. There is only so actually here you see it's a concatenation, so it adds additional channels. But the funny thing is that if you try to do this experiment and you try to concatenate features from input from encoder to decoder, the outputs are exactly the same quality as just doing the addition. So. And if you do addition, you don't need to have extra channels, no memory consumption. So you will see that the addition is the way to go, basically. That's why everybody is doing addition. It has many benefits. First of all, no memory use. Second of all, gradient. So if I have there a new block, then the gradient is not transferred to this side. But if I have, like it is transferred, but it's not transferred the same amount. So, but if I have plus, then the whole gradient from this side goes to this side. So there is also advantage for training. That's the one architecture. The other architecture, which is very common and which I want to talk a little bit before we start coding. Fully connected. Let's see if I have some image to share with you. Let me think. I'll find something which is more interesting. Okay, yeah, I think this one will work. So the alternative is actually fully connected neural networks. So, and we can actually make the units also fully connected. So what means fully connected? Let me not fully connected, but fully convolutional. So FCN means fully convolutional model. And fully convolutional model is one feature is great. So what is great? So great is it is the that any size input for training and inference. So the fully convolutional networks. So what they have, they do not have any. So do not have any linear layer basically. So if you have only so conv 2D and no linear layer. So, and actually you can do it. So if you remember those equations which I showed you where you can calculate the outputs, you can reduce it to this size here and just then skip any kind of layer in between linear and just pass to the other side. So imagine if I went down to so batch, comma, channel, comma, let's say 1 by 1, and then I going to the other side where I also have batch, channel 1 by 1, and I do not flatten anything in between. I just start building up the model. It's definitely not good idea to go to 1 by 1, then it will not be possible to work with any size. But if I go down to, let's say, 32 by 32 and then restore it from 32 without any flattening layer in between, then I'm ending up with fully convolutional model. And this can be done with these skip connections or without the skip connections. So if I don't have any skip connections, then it would be considered just a FCN. If it has skip connections like that, then it would be more like a UNet. But it works. It is not the best architecture, but it works, and it has these bonuses where, for example, that any size. The only downside is that when I train it, I need to make sure that my batches, all batch, have all of the same size. It is not possible to load in the PyTorch tensors arbitrary size samples in batch. It all needs to be the same size. So that is one downside. That's why you have this that's why we have the zero grad function, because we can virtually pass 1 by 1 sample with different sizes and then execute the gradient descent. So that's one. But then there's also some downside. I don't think we talked about that much, but basically you can use also fully convolutional models for classification. For example, like in the end, where we have the softmax, maybe I can find some example. So if I have the softmax at the end, but before the softmax I don't have any linear layer, I can do it. Like I can literally, calculate all of the reductions in the feature map size, so I end up by 1 by 1 by channel 1 by 1 image, right? And then I can do the classification, and then it has some interesting properties which I will show you. So here that would be this would be the normal classification architecture. So, and then if I'm removing, so this is the fully connected layers. If I'm removing these, check, remove, and make sure that here the last layer is 1 by 1 by 1000. In this case, if I have the classes like that, then this would be a classifier which still works. Or maybe even if I want to have any kind of size, then what I can do is here, we already talked about these guys. There's the adaptive average pooling, or max pooling, but in this case probably average. Adaptive average pooling, pool 2D, which makes sure that the output is always 1 by 1. So any size goes 1 by 1. So this allows me to classify different size images with pre-trained model without changing the model itself. And this gives me this fully convolutional architecture, FCN. It works for segmentation, it works for classification, but it has one downside. Maybe it's even a feature, it depends on what you want. So, but the feature is this, basically. You get for example, if I have the face prediction, so FCNs will predict 100% this is a face and also this is a face, because it has the the local connected layers, the convolutions, which have some kind of maximum window of attention. So we will talk about attention in more detail in the leftover sessions, right? So we don't have that many left, but still. So this would be the, let's say, the most largest area of the attention. So it means that the pyramid here grows and takes the area of which I can attend to with convolutions, maybe that size. If I construct the architecture like very deep, maybe I can make it larger, but probably it's quite difficult to do this just with convolutions. And if that is my size of attention, then it's basically collecting all of that information in my adaptive average pooling, and it will just say that this is also a face, because we don't have any fully connected layer which pulls together all of the features. So that's something to also keep in mind. But today the main focus is here to the UNet architecture, which is the most stable and most simple one. So let me open the task, and then let's try to build it. And yeah, and then I will talk a little bit more about the instance segmentation. So this is called semantic segmentation. And then for the home, we can do the so for the home we can do the semantic segmentation YOLO type models to play around. So let me see. So there will be the implement UNet model with not concatenation. I don't like concatenation. With addition. So let me share that one. Okay, I actually have this zip file. Remember, for once we had the problems with Moodle, RTU Moodle, and then I started to post everything. Oh, okay, let me just post it with zip files, but that will be fine. So do we have like lecture 10? I don't know, what is the, yeah, 10. So but those of you who survived so far, like congratulations. As you see, many moved to the business course because they didn't have the capabilities to continue with these mathematical topics. The thing is that that this is actually not that deep course actually. So those who want to keep working with these things, highly recommend to join the January course, where we'll repeat some of these things and go much deeper. So assignment 10.2, copying it in the Moodle. So 10.2 copied. Interesting. It seems that my first iteration was without the fully connected in between. Okay, cool. Let's see. So I will open also myself the template. And the equation. Okay, the equation, I really hope there's no bugs, so we'll go through it. But the equation looks something like this. With the upsampling strategy, and it's, yeah, so this is actually FCN, so there is no fully connected in between FCN. Also, which is interesting, that there is a sigma here, sigmoid. It says that this will be BCE, the binary classification. Okay, so please get the template. If you have errors, then we'll try to help you as much as I can. when we do this in live sessions, then we can help it a little bit more. So, okay. Just a second, I will open the task. The task is opened already. I'm just opening the pie chart. We need to find the task. Not that easy. Just a second. Okay, I found it. Open with PyCharm. Hopefully we'll be able to run it without much problems. We'll see. Okay, let's look into. Okay, we have one dataset. Okay, I was not sure which dataset I have because I have a couple of datasets to play around. Okay, let's try to go back here and show you the dataset a little bit visually. So the long dataset means that I want to classify the longs in the X-ray images. So, and then if I classify the longs, then I can basically do all sorts of like anomaly detection, pathologies, and so on. So this is like very simple type of segmentation task. So that's that. By the way, if somebody thinks that this is something to do easily for hospitals, the thing is that if you would like to do any AI models for medical, then most cases you need the certification. Certification costs huge money and it takes many years. So that's one of the reasons why medical establishment is a little bit lagging behind with all of the innovations. So the res block. So we have a res block given. Then the UNet, right, and then we just need to implement even given the convolutions, the up convolutions, right, but it seems that, right, so the res block is just changing the channel count from one to other. The output channel is 1, so this is the final output. And then we predefine the upsample and max pool. So it can be actually also average pool, it doesn't matter that much. So that's that. Then we have the training procedure, we need to implement the BCE loss, and finally do the training. Okay, cool. So let's try to implement this. I believe that many of you who actually are alive in this course can implement it yourself, but just for the time sake, I will show you a couple of these things in the course which I'm running in January. Probably people will implement these things totally by themselves. Maybe I can, so anyway, I probably need to show something here. So let's see, so this is a UNet, yeah, cool. Okay, let's try to do this. So, okay, so there will be the out. So there's some kind of out variable that will follow along the way. So, oh no, let's start with skip 1. So we will start just connecting from the first layer and then down towards all the layers. Self, convolution down, right, so that's that. Forward, again, please do not call the call operator. It makes code unreadable. Very difficult to follow if you not try to make it readable. So X, the image input, out, so self max pool. Do I have the max pool in there? Yeah, I have the max pool. forward skipo, so we'll give it here. And this is very similar to the ResNet and Inception net and Efficient net and all sorts of nets where we have custom mathematical paths to different parts of the functions. So basically, like these skip connections will travel to the decoder part. So let's do that. Actually, I can just copy, I think, these things and start changing it to 4. So this will be 2, 2, 2. The max pool is always the same because it is not being trained. So there is nothing to train in the max pool. But there is actually a fun thing. Like, it's probably possible to reuse some kind of trainable function many times as well. It's just the question is, why would you need to do this, and what would be the advantage? Might be that something is there, but I don't know. Maybe if there is some kind of, there are some models where you try, like it's called pyramid models, I think, where you have the, so the inputs can work in different sizes. You usually have the augmentations where you change, you definitely need to put large cats, small cats, so that it recognizes the cats, but sometimes architecture itself tries to able to classify objects in smaller and larger sizes. So maybe there some kind of function which repeats in different scales could be interesting. So, but in many cases you don't care about that. Okay, so then out self middle. Do I have middle? Convolution middle, yes, forward. And I think there will be just this last skip connection, skip 4. Also, the last max pool actually does not exist here. Cool, and now we're going to the other side. Another side is even more interesting. The one thing which doesn't work, I will show you. So this works if you write it like this. The PyTorch, for some reason, have not implemented properly this operator. They say that this is in-place operation, which doesn't make much sense. At least I think it's like the same thing. Like the in-place operations usually are the operations which are optimized for better performance, but it could be easily detected, in my opinion. I don't know why they have not implemented it. So that's that. Then we do the mirror size on this mirror output on this end. So then everything becomes out here, I believe so. Here will be out as well. Great. So then we will start chaining up samples. So up sample, it must be perfect mirror, otherwise it will not work. And you see this is already FCN. So FCN, there is no fully connected linear layer in between. So this is FCN type of model. Sample, so out equals out plus skip 3, I believe so. And then again, so this is down, there should be up. So there should be up 3. And now I believe this thing is copyable. So this is like something that I can copy a couple of times. So 2, 1. So this will be, yeah, we'll try to make that everything is just in one window, sorry. So this is 3, this will be 2, 2, 1, and 1. Believe so. Yes, maybe I have mistake somewhere. If I have mistake, I will have error. So, and then finally the Y output goes to the sigmoid, and it can be actually something else as well. As long as it gives me the outputs from 0 to 1. It cannot be softmax. It doesn't make sense to add softmax there. Like because there will be just one channel output, it will just fail, there will be error. So, but it can be maybe some clipped function, something else. So, but again, this is not much scientific value to study the probability distribution modeling functions. There are other opportunities. So as soon as we will start talking about the transformers very soon, then maybe you will see that transformers are also very far away from best architecture. There maybe you can invent some good ways how to improve transformers, for example, if you want to work on that. And so this is that part. Okay, let's go back here and then the loss function. So this should be binary cross entropy. Is my binary cross entropy. So this will be should be quite simple. So there's one minus and the other end, just that. So right, actually we could make it even more interesting. Okay, just realized. Just let me think. Do we have weights somewhere? The class weights are actually also important, but I'm not sure. Do I have weights somewhere? So weight. No, I don't have. So the weights would be calculated by the pixel count. So you would calculate the, before training, what are the proportion of the pixels in both of the areas. Like, I mean, on both of the classes. So actually I want to make note because I'm right now working on similar models. So weights for classes. So that's something to actually add here. So to do weights for classes. So and per sum of pixels, basically, not the samples themselves. So that's something too valuable to keep in mind. Let's then, so okay, so this will be minus torch mean. It can, minus sign can be also in the middle, but doesn't matter. So then I'm just thinking about the okay, so it should be y, and I actually don't have y prime anyway, so y prime equals model forward x. So there will be this function, so the y multiplied by torch log of y prime plus epsilon e minus 8 to stabilize it by the 0, plus then the 1 minus y, and then this thing multiplied by 1 minus this. Okay, cool. It should be like that. So yeah, so the weights are missing here, the class weights, and we'll see in a second that there are some other ways how to improve it. Let's see about the accuracy calculations, IOU. Do I have IOU somewhere? I don't have IOU implemented, which is also not cool. So, but the IOU can be implemented just by, you know, the filtering out and summing the pixels. So let's see. So let's try to run it. See if I have some errors, and probably I will not be able to train it properly on my computer because I don't have GPU. Oh, I have errors. This is not cool. Okay, we'll see. We'll fix it. Okay, so what doesn't it like? So the convolution down to, maybe you already fixed it. Let's see. So convolution down to, there is something wrong about it. 1 to 8. What did I make mistake here? So So why it says convolution 1? That doesn't make sense. Oh, right. No, doesn't make sense. Oh, there's something wrong here for sure, because I see that out values are not being used anywhere. So there's something wrong here for sure. So yeah, so yeah, I see. Here I left X everywhere. Sorry. So that's my bug. Yep, so I will update it again in the whiteboard. So these are easy bugs when basically just when you need to, when you can easily find it like that. But the difficult bugs are the case when mathematics execute, right? Like everything kind of works, you can run it. It gives you even some mediocre result, but actually your mathematics are wrong. Then that's a bad bug. So again, something still is wrong. This is annoying. Out 4. So here something is not right still. How that's possible. So let's try to look at that. So out 4, con down 4, but it doesn't like. So 32 channels, 16 channels. So I messed up something with channels. So the skip, alright, skip here, another bug, right, something even scrolled me up here. So another bug, 2 times skip here, so there should be skip 3. Really not really awakened this morning, lots of bugs. I will update whiteboard once again, lots of changes. Updated whiteboard once again. Let's try to run it again. Run. Oh, man, come on, why? This is super annoying. Oh, I fixed it. What is wrong again? Okay, now we have the problems on the other side. So the up channels are now wrong. Let's see. Yeah, I know where the problem is. So the initial task which I wanted to show you was actually to doing the concatenation, not the summation. So just like a dense net concatenation. So I just wanted to skip that part and let's just move to the summation. So, and for summation here, it must be the mirror of the encoder. So there is a bug here that the channel count must be 2 times less than it is. So like that. Please fix these 4 lines. I will put this on the whiteboard as well. So that the channel sizes are the right ones. Okay, we'll do that. Hopefully the 3rd time will not fail. Okay, it's training. Okay, cool. So it is training. It will not be great results, I believe, because I don't have CUDA. I mean CUDA. CUDA is available. Do I have somewhere? Oh, but it's not that bad. So the dataset is not split and it's still being able to do something. I guess the dataset is small, so we'll see actually something immediately. So 43% of the loss. So let me try, can I make it larger? So you see we have the first row is the ground truth, the second row is the predicted, the third row is ground truth, the fourth is the predicted. You already see that it is very, very good. So of course there are some problems, but you see it's quite nice actually. So if you add proper the IOU and other kind of metrics, you will get even better result. So that's what we want to get. So and it's even training on CPU. So that is because dataset is small, it works even on CPU. So please get to this point. For the homework, I will make that you add in the middle part you add the linear layer. So that's an easy task, right? So linear layer to adding the linear layer in between. What is shared right now? Yeah. So we'll do that. Let me stop the training. So you will add the linear layer and then maybe play around with the instance segmentation models. We'll see if I have a task on that. Oh, before the instance segmentation, I just wanted to show you one more interesting thing. So often what you end up doing is you end up making the loss functions for these models. So there's actually different flavors of UNets. Let me show you. So you can make these also if you want. So you can have the UNets with just one skip connection, with many skip connections, with dense-like skip connections, with all sorts of skip connections. So UNet++, UNet 3+, and whatever. So all sorts of those. Then another thing what you can do to update instance semantic segmentation is to start playing around with loss functions. So if I have the loss function with binary cross entropy, I can start adding some other loss functions, composite loss functions, basically, to add basically some other things which emphasizes basically other features. Trying to find, do I have the equation for dice loss? So dice loss, I remember, was something like 1 minus f1, I guess, or something like that. Let me try to find it. So okay, it's a little bit slow. Try to find it. Okay, I have those dice loss. Yeah, dice loss. Right. So this will be the dice loss. So it tries to work on pixel level to yeah. So basically, it's kind of like behaving in F1 type of manner, so that it tries to balance out between different class sums, basically, so that one class is not dominating everything. So the BCE, as I showed you before, dominates the output. So it has the just 0 or 1, and this makes it less dominating, the softer output. So that's one way how to achieve that the output is softer. So, but there's like huge universe of all sorts of loss functions. So if you look at what kind of options do we have, we start from the cross entropy, then we have on the other side dice loss, Tversky loss, focal loss, then on the other side we have boundary-based losses, region-based losses. You even see how they are called. So, and this actually dice CE, it's compound loss, the same thing which I'm showing you now, where you can combine the region-based with the BCE. So that's something very useful, often used. Last time I started to talk about the variational autoencoder, where you also have reconstruction loss and KL loss. So usually loss functions are not just one loss function, it's a combination of many, and you add some kind of coefficient to balance out which, like, do I want this output to be softer or sharper, for example, things like that. So that's another thing you can play around, and I will add more information how to do this. So that's that. Then next let's talk a little bit about the instance segmentation, about how these models like YellowRobot work actually. So the UNets, we understand now how they work and we are able to build them. But the instance segmentation works a little bit different way. So they have multiple output heads, and one head is predicting the confidence of object classes, another head is predicting the boxes, and the box head is the most complex one because it's really it is not that simple in a sense, but so, and it's also not stable. So for example here the box head, how it works. So the box head is actually also not rocket science what it has. So for each of the grid cells, so they define specific grid. So they say that for all of my input image I will have grid of box outputs, and for each of grid cells I will have some parameters for boxes itself. For example, each cell will produce let's say the dx, dy, width and height, for example. So that's one option how to do this, and it will sell not just that, but maybe it will produce 3 times this. So there will be dx1, dx2, dx3, and so on. So it's like arbitrary. So it can produce, let's say in this model, it will produce two of those for each cell. So there's like literally the hundreds or even thousands of these things. So this is 2, this is 1. So it, and the dx and dy, as you can imagine, means delta offset, and then width and height, how wide and how high is the box. So, and for each of these boxes I will do that, and maybe for each of the regions I will do the classification of that region. Just that part is simple. The classification part is simple. The boxes are complex because I will get literally maybe thousands of boxes for each of the paths. But then how then I can determine which are the right boxes, for which boxes should I pass the gradient, and which boxes should I, add as a result at the end. And for that part, there is a algorithm which is called the non-maximum suppression. So it just calculates all of the pairs and tries to find the pair, so tries to find the box which covers the most I of u in the given area. And it will take all of the boxes from all of the regions around it and try to just end up with a lot less boxes where we have the most overlap. So this is just like an algo based on I of u. And then this is actually interesting because this is part of the training. So imagine every time when you do the forward pass before doing the backward pass, you have some kind of algorithm inside that decides which outputs I will pass the gradient through. So, and this is also used in inference, in training and inference. So and then in the inference, it is, you can also add the threshold of confidence as well. By the way, I think the algorithm also takes the confidence as a input. Don't remember exactly, but I think it is. So that's that part. What else? Yeah. So I will try to find this pipeline, so I can give you that as a task to play around. But basically, this is the kind of like the way how YOLO, faster RCN, and so on works. YOLO CN SSD. The faster RCNN works with even with the masks. So the mask space, you can imagine that. This head, and by the way, what means heads? Heads, hopefully by this moment you already understand that the model input can be anything, the model output can be anything. So, and if model output can be anything, so why not just cut this into two parts, reshape it into the boxes, right? Like just dy dx width height, dy dx dy height. So basically I can reshape my outputs in any way I want, use them in any way I want, and this is the case. So they reshape one part as this and reshape other part as this, and that's why it works. So, and for the mask type of models, they can reshape this part just to do the same task that we just did with the lungs. So that's about it, how this things works. So next time we will talk about the recurrent neural networks, RC and LSTM. We can look a little bit phased LSTM, GRU units, all sorts of those things. I will try to find time to look also at the state of the art recurrent neural networks, because some of them are as good as transformer models, but like way more efficient. Like they need so much less memory, like I think 10 times less memory than the convolutional models. But the accuracy on the large language models are about the similar. So we'll look at that as well. So that's for the next time. Now for today, as I say, I don't have super much time right now, but hopefully this was useful. Let me look at the chat. Okay, so yeah, see you next week. I will post the where and how we will meet, most likely online, because I will not be in Latvia again, and then those of you who want to follow up, I will follow up on emails on the master thesis, bachelor thesis, and things like that. Just don't have time, but I will do that. So let's see you next week. Okay, bye bye.